Good morning, doctor, and my fellow friends. My name is Wei, and today I would like to talk about an alloy called iron aluminum alloy. So, what is iron aluminum alloy? Iron aluminum alloy, or also known as ferroaluminium, is a type of alloy that combines with aluminium and iron. In this video, we would like to talk about the properties, the microstructure, its application, and methods to improving its mechanical properties. So this is our group member. We have Guowei, Weilun, Nurain, and Chaoru. So what is iron aluminum alloy? Ferroaluminum alloy is an alloy consists of iron and aluminium. It usually consists about from 40 to 60% aluminium, and the applications of aluminium is wide, including like hard-facing applications, reducing agents, thermal reactions. So what are these mechanical properties of iron aluminum alloy? The aluminum alloy has attractive materials that exhibits good oxidation and sulfidation resistance, excellent resistance to abrasive wear and erosion, high strength, high hardness, tough, and less ductile. So as you can see here, this table below it shows some of the properties such as Young modulus, Poisson ratio, hardness, yield stress, compressive strength limit, and mass density. So what are the applications of iron aluminum alloy? Iron aluminum alloy has wide range of application, but in this video we will only talk about three of them. The first one is about turbine blades and components. Why aluminum alloy are used to make turbine blades and components, which is due to its ability to withstand high temperature and oxidant. These alloy are used in turbine blades and other components in jet engines and gas turbines. The second thing is about the engine component. This alloy is used for making lightweight components such as pistons, valve, and exhaust manifolds. They are lower in strength and reducing the overall performance of the vehicle, improving fuel efficiency and performance. The third one is about implants and prosthetics. So research is being conducted on the use of iron aluminum alloy in biomedical implants and prosthetics due to their biocompatibility and strength. So after talking about applications, what are the methods to improve the mechanical properties? So improving the mechanical properties of iron aluminum alloy is crucial. It expand their applicability, enhances performance, increase their competitiveness compared to other materials. What are some importance of this improvement? We can increase the strength, improve the fatigue resistance, elevate the temperature performance, corrosion and oxidation resistance, and enhance ductility and toughness. In this video, we'll only talk about 5 of them, which are precipitation hardening, surface treatment, heat treatment, grain refinement, and altered element content. The first one is surface treatment. There are many methods about to do this treatment, such as chemical treatment, electrochemical, heating. So what is surface treatment? Surface treatment is essential to enhance the surface properties such as corrosion resistance, wear resistance, and aesthetic appeal. Various surface treatments can be applied to iron aluminum alloy, each tailored to meet specific requirements. The second one is alter the content of the element. For example, adding chromium, manganese, titanium can enhance their specific properties such as corrosion resistance, strength, and ductility. What are the importance of altering the content of element? It is to enhance the various mechanical and physical properties such as strength, ductility, corrosion resistance, and high temperature stability. The third one is heat treatment. So heat treatment is critical process to enhance the mechanical properties such as strength, hardness, ductility, and resistance to wear and corrosion. The specific heat treatment procedures can be based on alloy composition and the design properties, but the general steps typically include certain treatment, such as heat treatment, solution treatment, quenching, annealing, stress relieving, and precipitation hardening. Grain refinement. So grain refinement is always a critical process to enhance their mechanical properties. The goal is to produce a fine and uniform grain structure, which typically result in improved strength, ductility, resistance to cracking, and toughness. Finally is precipitation hardening. So the purpose of precipitation hardening is to increase the strength and hardness, improve the wear resistance, and enhance the high temperature performance. So the heat treatment is the purpose is to create a fine dispersed precipitate within the iron aluminum matrix. So this is the phase diagram of iron aluminum alloy. In the next session, we're talking about the microstructures of the iron aluminum alloy based on different percentage of a material. That's all for me. Thank you very much.
Hi doctor, my name is Ong Wedun. Today I will continue the presentation of microstructure of alloy at 25% aluminum. The alloy with 25% aluminum means that the alloy content of 25% iron and 25% aluminum by weight. Now we can locate the 25% aluminum composition on the FEAL phase diagram. From graph, we can see that the microstructure transformation and solidification process can be divided into four steps. Okay, for the first stage at 1500 degrees Celsius, the microstructure of the alloy is 100% decay. Now, and then we'll continue to cool down until it reach the liquid temperature is 1400 degrees Celsius. The first solid phase begin to form. For the 25% aluminum, the primary solid phase is usually a body-centered cubic phase known as ferrite. Then it will come to stage 3 when the temperature come to 1355 degrees Celsius. The liquid will totally transform into the alpha ferrite. Then the microstructure will only contain the alpha ferrite. Then if when the temperature continue to decrease, it will come to the test fault, which at the 1200 degrees Celsius, the microstructure transform from alpha ferrite to FeAl. The microstructure exits as a solid phase of composition 25% aluminum. You can see that for the aluminum, it is a red color and iron is a white color area. Now we come to the cooling curve of the 25% aluminum alloy. From initially, the alloy will in the form of 100% liquid and it will continue to cool down until it reaches the liquid temperature is 1410 degrees Celsius, and at this moment the solidification of the alloy will start to form. And we can see that in this phase the microstructure will contain the liquid and the alpha ferrite. That means that the microstructure will with these two elements, and when it reach the 1355 degrees Celsius, all the liquid will transform to the alpha ferrite. That means that microstructure will only contain the alpha ferrite. And it's stage 3, and we come to the stage 4. When the temperature is lower than 1200 degrees Celsius, the alpha ferrite will start to transform to aluminum and iron, and the composition will contain 25% of aluminum. Now we come to the composition calculation. At 1200 degrees Celsius, you can see that the composition of alpha ferrite is 96%, while for the composition of FeAl plus Fe3Al is 66%. With the calculation, we can clearly see that for the first fraction of Fe3Al, the percentage is 11.76%, while for the aluminum, the first fraction is 88.24%. It's the end of my presentation. Thank you.
Hello, I'm Jess Hao-yu. I want to share the information about an aluminum alloy, which is about 60% aluminum. From the phase diagram, we can know there are five states we can analyze: above 1220 degree, 1220 degree to 1160 degree, 1160 degree to 1092 degree, and 1092 degree and below 1092 degree. I will talk about the microstructure transformation, cooling cover, and composition calculation. Now let's look at the first state, above 1220 degree. The microstructure is liquid phase. At this high temperature, the alloy is totally in the liquid phase. There are no solid phase present. And state 2, cooling from liquids flow to solids. As the temperature decreases, solid aluminum ion starts to form from the liquid. Theta grains start to nucleate. The microstructure consisting of a mixture of liquid and solid aluminum ion. The proportion of solid increases as the temperature drops. And state 3, the liquid phase is completely transformed into theta. And state 4, lambda microstructure consisting of alpha-2 and ferroaluminide start to form. The microstructure is theta plus alpha-2 plus ferroaluminide. And state 5, lambda microstructure completely formed. The microstructure is alpha-2 plus ferroaluminide. We can look Now we can look at the cooling cover. From the phase diagram, we can get this diagram. And this solution is liquid mixture cooling. And this point, theta solid solution began. And this point, theta solid solution end. And this solution eutactoid isothermal freezing. And this solution solid mixture freezing. And then we can talk about the composition calculation. And 700 degrees. There are two compositions, which one is ferroaluminide and another one is alpha-2. About the phase fraction of ferroaluminide is 60% and the phase fraction of alpha-2 is 40%. That's all for me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh to Dr. Noor Akmal. My name is Nurul Ain Shahidah and I will be presenting about the microstructure of alloy at 80% of aluminium. As we cool the FeAl alloy from its molten state, several key transformations occur. The FeAl alloy with 80% aluminium is classified as a hypoeutectic alloy since it has more aluminium than the eutectic composition of around 66% of aluminium. So at the temperature of 1410 degrees Celsius, the FeAl microstructure exists entirely as a liquid. So at this temperature, the microstructure is homogeneous and consists only of liquid. At the temperature of 1100 degrees Celsius, the FeAl begins to nucleate at the liquidus line. Being a hypoeutectic alloy, the primary phase that starts to form is aluminium. The microstructure consists of liquid with Al nuclei is forming. At temperature of 654 degrees Celsius, the Al continues to nucleate and form a lamellar structure near FeAl3. The eutectic reaction occurs at this temperature, forming FeAl3 and Al from the remaining liquid. The microstructure consists of primary Al with eutectic Al and FeAl3. Next, the alloy solidifies completely, consisting of FeAl3 and Al phases. The final microstructure consists of a primary aluminum phase and a eutectic mixture of aluminium and FeAl3. So this is the cooling curve of the process of solidification that I have mentioned before. So this is the graph of temperature against time, and we can see the temperature of 800 degrees Celsius, which is the liquidus line, and temperature 654 degrees Celsius approximately as the solidus line. So about the phase fraction, the composition of each phase, which is FeAl3 phase, it is an intermetallic compound, and the composition of FeAl3 is about 34% of iron and 66% of aluminium, while for the Al phase or aluminium phase, it is purely aluminium. So the composition of aluminium is of course 100% of aluminium with 0% of iron. So given the data of 4 grams of FeAl3 and 30 grams of Al, we can calculate the phase fractions based on the formula. So after we have calculated based on the given data for FeAl3 and aluminium, we can see that at 500 degrees Celsius, the FeAl3 phase constitutes approximately 11.76% of the total mass of the alloy, while the Al phase makes up approximately 88.24%. So that's all from me. Thank you. The FeAl alloy exhibits excellent strength, high temperature resistance, and good oxidation resistance. It possesses a unique combination of mechanical, thermal, and chemical properties, making it suitable for a wide range of applications. For example, it is suitable for moving parts such as turbine blades, and it is fuel-saving due to the lower weight of FeAl. Next, it has better corrosion and wear resistance, so it has less maintenance and longer lifetime. The excellent corrosion resistance may also enable higher operation temperatures, thereby further reducing energy consumption. For large industrial facilities, support structures could be much leaner. For example, for a steam cracker, FeAl tubes would be employed. At different stages in phase diagram, different things can be observed, such as isothermal reaction, intermetallic compound, solid solution, solidification process, cooling curve, and microstructure. In conclusion, the FeAl alloy serves wide range of applications such as aerodynamics, structural engineering, biomedical fields due to its outstanding properties, and engineers and scientists are actively to do research about this alloy to broaden the scope of its future applications. That's all from our group. Thank you.